Welcome to Walk Like a Mathematician learning task. In this task, you're going to be taking what you've learned about matrices and going to the next level. Primarily, you'll be looking at some of the properties related to matrices that we kind of take from algebra. To show those properties, I'm going to scroll down here. So the commutative property, as you can see here for addition, is looking at, for instance, 2 plus 3, and then saying that by addition, if the 2 was the A and the 3 was your B, when you switch the 2 and 3, 2 plus 3 is still equal to 3 plus 2. Now we do the same, or we use the same property with matrices. Say we had a 2 by 2 plus a 2 by 2. As long as we switch the same matrices, we still have a 2 by 2 and a 2 by 2. When we add those two matrices, we get the same result. Now, the same kind of works for multiplication of matrices. But with the commutative property, it's not A plus B, it's A times B with multiplication. So A times B is equal to B times A. The associative property for addition seems to work as well. You have A plus B, and with the parentheses showing, that means that you would take the A plus B first. Then you will move outside the parentheses and add your C. I'm just going to zoom in a little bit. Hopefully that works for you. Now, we are going to say that when we take A plus B first and then add the C, we would get the same result if we were to add B and C first, then the A last. Now, if you would like to check that, of course, I'm not going to give you the answers to your own investigation. I want you to try it out. Try to add three matrices. On the left side, add the first two. On the right side, add the last two. Then for both sides, add that last matrix, and I'm pretty sure you're going to get the same result. With multiplication, though, the associative property gets a little tricky. And it gets tricky when the dimensions need to match up, and then even after they match up, you might get something totally different. For instance, let me look for my pen. Let's say we had a 2 by 3 times a 3 by 4. I'm sorry about that. And we're going to do that first. Let's say we put that in parentheses. Then we had a 4 by 1. And I know you love that sound effect. So the 2 by 3 works. You get a 2 by 4. Sorry about that. And then you're going to end up multiplying that 2 by 4 times a 4 by 1. Your final answer for, if this was your left side of A times B times C, on the right side, you would get a, well, you would do the 3 by 4 and the 4 by 1 first. So you would still have, and I didn't mean to move my window. It's not moving. I got it. So again, you would have your 2 by 3. Well, let me do this. I'm just going to get rid of all of it, you know. Alright, so you have your 2 by 3 times your 3 by 4 and your 4 by 1. Alright, so the 4's cancel out, so you have a 3 by 1 now. And that's cool, because then you still have your 2 by 3. And at the end of the day, you'll still end up with a 2 by 1. Will this always work? No. I don't think you heard me, but if you did, obviously you have a little bit more insight than those that did not. So now let's talk about identity matrices. It says that there exists a unique real number 0 such that A plus 0 equals 0 plus A, which equals A. So that's pretty much saying you would have a matrix, and when you add an identity matrix to it, or at least zeros to it, you get the same matrix. Nothing changes. There's also the identity matrix or matrices for multiplication. When you multiply a matrix times the identity of it or a specific type, you still get the same original matrix. In terms of addition, the only way that a matrix can stay the same and you added a matrix to it is that you have your matrix A, let's say it's a 2 by 1, times, or let's say, I'm sorry, plus 0, 0. Okay? 2 plus 0 is 2, 1 plus 0 is 1. But with multiplication, let's say we had a 3 by 2. Let's go 4. Let's go 6, 2 by 2, just to make it simple. The identity for that one would be 1, 0, 0, 1. Ooh, something new for you. I want you to check that out. Multiplying the 3, 4, 6, 7 times 1, 0, 0, 1. So now let's scroll down to the rest or through the rest of the task. Let me zoom back out. All right, so you're going to use all of these matrices on the top of page 2 to then look in or answer the question, are matrix addition and matrix multiplication commutative? Does it always work when you switch matrices? What would matrices have to look like in order to be commutative under addition and multiplication? There are certain requirements that must be met in order for a commutative property to apply. And then in general, any two matrices that can be added will be commutative under addition. Are matrix addition and matrix multiplication associative? I gave you an example of where I think I only showed you multiplication, that it did work, but I made a comment about it. If you didn't hear it, make sure you go back and play it over. So in number 4 and 5, you're working with the 0 or identity. 4, 5, and 6. You're working with the 0 or identity matrices. And then in number 7, they start to show you about inverses. Before I show you what an inverse looks like, let's see if they show it to you later. They don't. So let me go ahead and open up. I don't have that. I'm going to kind of show you. I know what I can do. Give me a second. In order to find the inverse of a matrix in your calculators, depending on what type of calculators you have, I know there's links to an online calculator in your course, but on the graphing calculators, you can type in this to represent your first matrix, or your A matrix A, letter A. Notice I use this little power of -1. That's telling your calculator to find the inverse of whatever matrix A is. As one of your standards in math, accelerated math 2, you are expected to be able to find the, what could you refer to it as? The inverse of a 2 by 2 matrix by hand. And so you would use this formula: 1 over your determinant times whatever the A was is now going to be D, whatever your B was times -1, whatever your C was times -1, and whatever your A was is going to switch spaces with the, sorry, I clicked the button I did not intend to click. But again, your A is going to switch places with the D. All right, so let's say we had a matrix that was 3, 7, 4, 5, and we needed to find the inverse for it. We would put the 3 and the 5 here. 3 times 5 is 15, minus 7 times 4 is 28. Okay, you do the arithmetic. Now the 3 was here, but now we need to put the D. The 5 goes here now. The 7 stays, but it needs to change to a -7. The 4 changes, needs to change to a -4. And the 3 that was here needs to be here now. Again, the 3 and the 5 switch places all together. So with 3x3s, you do not want to do them by hand. Use some technology. Earlier with, what could you say, finding the inverse of matrices, I talked about the determinant. So let's pay some attention to what the determinant looks like, how you can find it, and how you can recognize its representation or symbol. Notice this looks like absolute value of A, or absolute value of A, B, C, and D, a matrix. What you're supposed to do is take your majors. I'm going left to right. I refer to that as your major. And then I'm going to go right to left. A times D, B times C. Major minus minor. AD is your major. BC is your minor. Now you kind of follow the same process with 3x3s. Notice you have A, B, C, D, E, F, G, H, and I in a 3x3 matrix. But you will run out of space. You'll run out of values because you're not going to be able to find the determinant of a 3x3 using the same process to the T. You have to kind of adjust it a bit so that it works for you. Now, notice the first column for this 3x3 was A, D, and G. What you're going to do is you're going to place another column to your 3x3. So you change the 3x3 to a 3x4. But you don't only use that first column. Use the second one as well. And once you do that, you're going to be able to take your majors, 3 of them, and then your minors, 3 of them, add up all your majors, subtract all your minors. Once you do that, you'll get a specific value, the determinant of your matrix. And in doing so, you might be able to find the area of triangles. So for instance, remember that I made a point to recognize the representation of a determinant. What you would do is, when you see these bars, these lines that look like the absolute value of your matrix, that means you need to find the determinant. Now when I mentioned finding the area of a triangle, it's using determinants that you can do so. Once you know the coordinates, your x and y, your x and y, your x and y, and write ones in that last column, you can find the determinant, and then in the same, what could you say, in the same step or in the same process, find the area of that triangle. It's just that once you find the determinant, multiply by half, some people say divide by 2, and make sure that it's always positive. You cannot have an area of a triangle that were negative. That's really about it for the rest of the task. I know in the task there's reference to the TI-84. That's not the best calculator out there. Casios are the bomb, and they're half the price. I certainly didn't receive any type of compensation from Casio or TI. I'm just voicing my professional opinion as a math teacher. Again, I'm done. If you have any questions, please be sure to ask your online teacher.